All right, one more example of using the difference quotient to calculate a derivative. This time we'll use a rational function. And the only difference here is that the derivative is going to be a little bit more complicated in terms of algebra, but that's about it. So here's our limit. It's going to be 1 over x plus h minus 1. Remember, we're just substituting x plus h in for x. And then minus 1 over x minus 1 all over h. And my strategy here is going to be to find a common denominator for this sum of fractions on the top. And so I'll just use the brute force method there of finding a common denominator by multiplying the two. So I get x minus 1 minus the quantity x plus h minus 1 all on the top. And then I just have the product of those two denominators on the bottom here. And I'm going to just slide that bottom h in the other denominator in here, because after all, dividing by h is the same as multiplying by 1 over h. So I think that takes care of it. Now I can just distribute that negative sign in the numerator so that I get x minus 1 minus x minus h plus 1 all over this denominator. And I'm not going to bother to multiply that out. Often you really don't need to do that in these kinds of derivatives. The x's cancel on the top and the 1's cancel, leaving me this minus h. So I'll rewrite that limit as h goes to 0 of just minus h over this same denominator. And I can see ahead of time that those h's are now going to cancel because that h is just multiplied on the bottom. So those guys go away. And I'm left with a limit that I think I can evaluate. It's going to be minus 1 over quantity x minus 1 times quantity x plus h minus 1. And when that h goes to 0, I'm just going to be left with x minus 1 quantity squared on the bottom. And so that's my derivative. The derivative of 1 over x minus 1, the rational function, is another rational function minus 1 over x minus 1 quantity squared. So let's try and graph those two functions. We'll graph the function up here, and I'll just do that quickly. You know how to graph rational functions. It's got a vertical asymptote at x equals 1. It's positive on the right side of that asymptote, negative on the left side, and it has a y-intercept of -1, so it looks pretty much like that. And one thing to notice is that the slope of this is always negative. On either side of that asymptote, the slope is negative. So we want our derivative to be negative everywhere. And in fact it is. It's got this minus 1 numerator and the denominator is squared, so it is going to be negative everywhere. Minus there and the squared. So if we graph that, we have our same vertical asymptote, but it's going to be, now this part over here is shifted down to the negative side of the graph, and the other side looks roughly the same. Of course, these will be a little bit steeper because the denominator is squared. But the idea is right. The derivative is negative everywhere, just as the slope of the graph is. And finally, this particular function doesn't actually have a derivative at x equals 1. There's no value of the function there. It's discontinuous, so therefore it can't have a derivative.